Hello, Kim students. I'm going to try another lecture. This one's going to be on Chapter 8, Acid-Base Chemistry. It's pretty long, so I might try to break it in two. But anyway, this is an important topic for us. It's a new way of thinking where we use curved arrows to show how reactions work. And there's a lot of things that we use to explain how the reactions work, which is the underlying organic logic. So we'll use things like Ka and pKa to make evaluations of equilibrium, and then we'll use inductive effects and resonance effects to explain those equilibria. Okay, in Chapter 9 we're going to use these same ideas, but we'll add in steric effects there, but all the other stuff, inductive effects and steric effects, will still be important. Okay, so on this first slide I have just some simple general acid-base equations according to what's called the Bronsted definition. Bronsted focused on protons. He didn't really care about the solvent. So a base for him would be a proton acceptor. So if you look down here, here's the base, and over here it's accepted the protons. Okay, and an acid for Bronsted would be the proton donor. So HA gave away the H, the proton, to B, and so when that happens it becomes the conjugate base. The base over here on the left side becomes the conjugate acid on the other side. And so there'll be an evaluation here. You'll notice as I go down I've changed little details, like the first two are neutral, but in the second one I have a protic acid with a positive charge. And then in the third one I have a negative charge on the base, so probably a little stronger base, but a neutral acid. And in the fourth one I have a negative charge on the base and a positive charge on the acid. So these are all general. Notice the two arrows, they're always required. We pick up the proton with these electrons, we have to push these away. So this is something you want to get down. It will happen over and over in this topic. I have some specific examples here, but I have those on the next slide. So here I'm using water as the neutral base to pick off a proton from HCl. This is a reaction from your freshman chemistry. So we know that HCl is a really strong acid. This is going to be a 100% reaction, making hydronium ion and chloride. Water is also our reference base and our solvent, usual solvent, so that's something else to keep in mind. But notice still the same two arrows that we used before. Here I have water reacting this time with a positive charge, the ammonium ion, but same two arrows, pick up a proton, make hydronium ion and ammonia. This one is in equilibrium because ammonium ion is a very weak acid. Maybe only about 0.5% dissociates like this, so this will be in equilibrium. HBr is a super strong acid, like HCl up here, and if I use hydroxide, it's going to be even stronger base. So if this is 100% up here, if it could be more, it would be more, but it can only be 100% down here. And in the last example, I have hydroxide, which is a pretty strong base, with the ammonium ion, but in this case, the hydroxide can completely remove the extra proton here and make water, the conjugate acid of hydroxide, and then ammonia molecule, which is the conjugate base of the ammonium ion here. These are all proton transfers. That's the Bronsted definition. These little arrows that I'm showing here, it's a new way of thinking. You're going to use this in organic and biochem and all the reactions that you study, so you want to get it down here. Okay, so in acid-base chemistry, like you learned in freshman chemistry, water is almost always the solvent. And so for our purposes here in this topic, water will be the reference base if we react it with an acid, and water will be the reference acid if we react it with a base. In freshman chemistry, you might have done both of these, but in organic, we'll mainly use water as the base. And then we'll have different acids that we look at, and we'll be looking at the stability of this conjugate base minus charge. Now, substances that can react both as an acid and base have a special name. So they could be called amphoteric or amphiprotic, either way. Not a big concern for us, but that is a commonly used word. So for us in organic chemistry, we focus on the electrons more and use curved arrows to show how they move in reactions and in resonance structures. So we've already used them in resonance structures, and now we're going to start using them in reactions. Easy in this topic, Chapter 8, a little more complicated in Chapter 9. When we get to Chapter 10, we'll have to learn yet another little way of using arrows, and that's when we move one electron in free radical reactions. Then the arrows will have a half of a head instead of a full-headed arrow. Okay, so here's a reaction where water is our reference base. That's real specific. But then the acid over here is general because we're going to put any kind of acid we want in here. And then we're going to evaluate the extent of this reaction based on the strength of this acid and the strength of the hydronium on the other side. Okay, and that'll tell us which of these conjugate bases can form, how much, the extent, how stable they are, and that'll help us out. We're going to use Ka values and pKa values. We'll talk about those in just a little bit. This is the other alternative. We could use water as a reference acid if we were talking about bases. So we will talk about bases, but we're not going to use Kb and pKb in our particular course, although you might have done that in freshman chemistry. But it's the same idea. We have an equilibrium, so we would write an equilibrium constant, and then we define this pKb. We'll define pK in just a little bit. So same idea. We'd be comparing the strength of this base here to the hydroxide base over here. Which one is better? But notice again, the arrows are the same. They come from the base lone pair to the proton and push the conjugate base away. For water, the conjugate base would be hydroxide. Okay, so you want to get real good at this arrow pushing here. It's real simple, but you want to get it just right. Another thing you want to kind of focus on is formal charge, where minuses are, pluses are, and neutral molecules. Okay, so for a lot of our reactions, there'll be more than one possibility. So things will be a little bit ambiguous, and that's what makes organic chemistry, I think, a little difficult. It's because sometimes there's multiple choices. If you're using good logic to get to right choices, I'm not so concerned that you might have picked the wrong logical choice. If your logic is good, you'll be right sometimes and you'll be wrong sometimes, unless you can make the subtle distinctions, but you'll still be in pretty good shape. Okay. I just want to remind you of resonance structures because we did a lot of arrow pushing there. In resonance, we're always pushing electrons. Those electrons are always in 2p orbitals. They could be pi bonds, or they could be isolated p orbitals, say a lone pair or an empty 2p orbital. Okay, the donors in resonance will be a lone pair or a pi bond, either one. And the acceptors in resonance are carbocations, which are missing 2 electrons, just an empty p orbital, 2p orbital, and pi bonds. So you'll notice pi bonds can donate and pi bonds can accept. As you go down through the examples, consider where that happens. First example, we have an empty 2p orbital next to a pi bond, so pi bond can donate. So we move the electrons over, make the pi bond on the right side, and now we have an empty orbital on the left, and you can see that that positive charge is spread over 2 different atoms. Electrons are spread out, so less electron repulsion. So this is going to be more stable with resonance. An example over here, I'm using a lone pair next to an empty 2p orbital, so I share those in to make a pi bond, and that's going to be a good thing because I give the carbon a full octet and I make an extra bond. So even though we have a positive on the carbon here, it's not as stable as having the positive on the nitrogen here with the extra bond and full octets. So these are 2 both very important resonance structures. This shows that the carbon can accept electrons, which we will do later on. I put them both together here, so I have the empty 2p orbital next to the pi bond, next to the lone pair. So you could actually push all the way from the lone pair to the carbon right here, and we have 2 pi bonds here. Or you could do it step by step. You could take these over, empty orbital here, bring these in. Either way is good. I wanted to show an example that's sp, because sp has pi bonds and p orbitals too. So in this case, I have a carbon that's missing a pair of electrons, empty 2p orbital. I borrow one of these pairs of electrons here in, and you can see now I have a triple bond. This would be the much better structure for telling me what is the hybridization of the carbon and the oxygen. Oh, and I see I forgot to take these electrons away, so you want to scribble those out. I should just have the lone pair here. But in any case, these would be sp atoms right here. Up here I might mention too, this nitrogen looks like it could be sp3, but if I look at this resonance structure where it has more bonds, it looks like it's sp2. Okay, so down here I have the opposite situation. I have too much electron density in a lone pair, and so I have an adjacent pi bond. So notice my donor is a lone pair, but this time the pi bond is an acceptor because I can push to the distant atom right here. So now the pi bond is between the carbon and the oxygen. So I have two different resonance structures. These are both important. The more important one has the minus on the oxygen because they have the same number of bonds and full octets. This is kind of the same, except this is a neutral molecule. It doesn't look like it's neutral because I have formal charge. But one of the oxygen has an extra lone pair and the other oxygen has too many bonds. So I can push these in, push the electrons over to the other oxygen. This looks almost identical, except it's the oxygen on the left that's minus here, and it's the oxygen on the right that's minus here. So these are equivalent resonance structures. It's going to be very stable that way. And this would be ozone. Okay, it's a gas. Down here I have a lone pair next to a pi bond, but this time it's a triple bond. So I push the electrons into the pi bond, push them over to the nitrogen. And you can see I still have the same number of bonds. I have 2 pi bonds here, I have 2 pi bonds here. And the minus is on the nitrogen here. That should be a little bit better than the minus on the carbon. But I do get my hybridization from this resonance structure. These are both sp. Okay. And for this guy, I think it looks like it's sp3 here, but if you look over here where it has more bonds, you can see that's sp2. It has to have a p orbital to overlap with the pi bonds. And this is an example of benzene, an aromatic compound, where it alternates pi and single bonds all the way around the ring, and you can shift all the pi bonds over one position. So it's really like, since these are pretty equivalent structures, it's really like I have a 1 and a double bond here. So that's up to about 1.5 bonds. So anyway, this is resonance, more use of curved arrows. So hopefully that helps you out a little bit. Okay, we also have a Lewis definition of acids and bases. Came out the same year as Bronsted. But Lewis, as you might guess from Lewis structures, where you're drawing in bonds and lone pairs, he viewed the world from a point of view of pairs of electrons. So his definition of acids and bases involved pairs of electrons. For Lewis, an acid was an electron pair acceptor. Okay, so you got to be careful because for Bronsted, an acid was a proton donor. So we got that word acceptor and donor on the same guy. But the Lewis acids is the one we kind of focus on. We will call them electrophiles when we get to chapter 9. So electron is negative, phile is loving. So Lewis acids they love electrons. Okay? They're going to be donated to the Lewis acid. Lewis bases donate pairs of electrons. So the acids accept a pair of electrons, the base donates the pair of electrons. So again, it's kind of opposite to the Bronsted definition, where a Bronsted definition says it's a proton acceptor. Okay, so easy to get confused. We're going to call these nucleophiles. Nucleo is positive, phile is loving. If it's donating a pair of electrons, which are negative, it makes sense that it should go to something positive. Okay, so I have a few examples down here to kind of show the difference. The first case is works very well with the Bronsted definition because we have an acid that's a proton donor. We have a good base here, electron pair donor, and so notice the two arrows are the same. So now over here there's the conjugate acid and the conjugate base. Bromide, by the way, is very, very stable, and that helps drive a lot of the reactions we talk about. Okay, so this is the acid-base reaction, but it also works by the Lewis definition. Remember, the Lewis definition is a base is an electron pair donor, and an acid is electron pair acceptor, and then we have to push the bromide away. So either way this works. However, when we come down here, the Bronsted definition fails, because I need a proton to be transferred, and I don't see it. So this time, the pair of electrons, just like up above in cyanide, is attacking the carbon because the carbon has the bromide leaving group. So that will leave, again, very stable bromide. But notice now the two carbons are joined together. So this is a very, very good reaction. We've taken cyanide and we've converted it into a nitrile functional group. Okay, so that's real good. We're going to do that in chapter 9. I have several examples here. I'm not going to spend a lot of time on them. They're reactions that we study later on. But mainly what I want to show is the electron pair donation to something besides a proton. So I can donate these electrons into this carbon because I can move the electrons over to the oxygen. That would give a temporary minus charge on the oxygen. And so we would have to neutralize that, what they call a workup step. And so this would actually be a Bronsted definition, because we could transfer the proton here. Arrows are still the same idea. This would also be a Lewis definition, but when the proton's being transferred, people tend to focus on Bronsted. This is strained epoxide. It also has an oxygen leaving group, which can take electrons away and release all the ring strain when we attack. So notice I have the same guy, electrons here, very powerful electron pair donation, pops this open, transfers the minus from the carbon to the oxygen. That's a good thing. But I have a minus oxygen. I did make a carbon-carbon bond, and then we'd have to do the workup step. Again, putting a proton on that negative oxygen. This is something really strange looking. We would have to make this. Okay, that's something we learned in aromatic chemistry. But if I made this, this is an electron pair acceptor. You can see it has a positive charge. I could take electrons from the pi bond, push these over to the oxygen, and I would have a nitro group. That's something we've studied. I would have a momentary problem here because the electrons, I would have a hydrogen on this same carbon, and then I would have stolen the electrons from this carbon down here, so it would have a positive charge. So I could come back in and take this proton back and remake the pi bond. So that would give me nitrobenzene. This is another kind of strange looking one because I don't even see a proton transferred in here. This is a bromine molecule, very reactive. I'm using the pi electrons again. So I actually have 3 arrows here. We won't worry about that until we get to alkenes. So I get a lot of transfer. I'm donating in. This is the base. This is the acid that accepts. I get a temporary plus charge here, like I did over here. So the bromine uses its lone pair to bridge across. And then the bromide that came off is an electron paired donor. So this would be a Lewis base, or we could call it a nucleophile. And since this is accepting, it could be a Lewis acid or electrophile. So I don't even have a proton involved here. I need the Lewis definition. Okay, so here we have a little problem. We want to show these reacting as Bronsted acid-base chemistry right here. So I have our little reference reaction up here to remind us with water. Okay, so can you put in those arrows? There's going to be some arrows involved. We come from the base, we go to the proton, we push these electrons away. Okay, so can we do that? You can see that right there. Right, so you should be able to write that. If we look at these two right here, it looks like I have a negative charge here. That would be a good place to push from because I could make it neutral on the oxygen. And down here I have a negative charge on the carbon. That would be a good place to push from because I could make it neutral. So these guys look real similar, but they would react at different positions. If you're very observant, you might notice that these are resonance structures. So the resonance structures, when you write the minus in these different spots, actually show you locations where reactivity can occur. Okay, so let's go down and take a look. So in the first one, if we move the electrons over, we go from this negative anion. We call this an enol, and then the ol comes from the alcohol. Enolate, 8 means minus charge. And we get what's called an enol tautomer. Okay, and then the conjugate base is pushed away. If I use this one here, I push the electrons over, pick up the proton, push A away, just like above, except this time on the carbon. And this is called a keto tautomer because it looks like a ketone right there. Okay, this is called an enolate, this is called an enolate. So you might say, how can that be when they don't look alike? And the reason is because they are resonance structures. They are truly just one structure that we need to draw to show where the minus charge is. And the minus can react from either side. Okay, the tautomers themselves are in equilibrium. They are not the same structure. And the way they get to go to the other one is they have to go into the equilibrium of the enolate and then transfer the proton to the other site. So this would be in the middle. Okay, this is what we talk about in organic. Organic is kind of ambiguous. We have multiple sites that can react, and that's what you have to learn to deal with. Okay, so these are actually isomers, different molecules. What if I didn't have those lone pairs? Could I do anything? Well, it turns out that if I have a pi bond here, the pi electrons can do the same thing. But now we run into ambiguity again. Okay, because if I push the electrons to the proton here, only one carbon can join up with the proton, and then I can push A away. So let's take a look. If I push the electrons like this, and I put the hydrogen on the right carbon over here, okay, that would give us this carbocation. But if I push the electrons and put it on the left carbon like this, that would give us this carbocation. So they kind of look alike, but if you're careful, you'll see that there's two R groups on this one and a hydrogen. And on this one, there's two hydrogens and one R group. So you might remember back to our earlier topics about inductive effects, R groups are inductively donating. Okay? A carbocation desperately needs electron density, and if I have two car groups helping out, that's going to make it more stable. This would be a secondary carbocation. Over here I only have one R group helping out, that's a primary carbocation, and the energy difference is so big between these two that we only react it this way. There would be a subsequent reaction, this would be like an alkene topic. Whatever A is with its minus charge could then add in here and complete the molecule, but that's not really part of this topic. Okay, what if we turned it around? Instead of talking about this guy being a base, we talked about this guy being an acid. So if this guy's an acid, I got to decide where is the acidic proton. And if you look at this molecule, it's not so easy, because I got 3 protons here. They're all on the carbon, so these 3 are methyl protons, all equivalent. I have a proton on the oxygen. I have 2 protons here, so the question is, are they the same or different? If this guy looks straight across, it sees an OH, and if this guy looks straight across, it sees a methyl. Those are different. So in fact, I have 1, 2, 3, 4 different types of protons. However, there's only one proton that's going to act as the acid. Remember, when I push the electrons to the proton, I have to push electrons away with a minus charge. And it would be much, much better to put the minus on an oxygen because it's much more electronegative than a carbon. So it's very clear where we're going to go. There's only one acidic site there. We'll go up there. And then you'll notice we make the enolate. That's just what we were talking about. Remember, on the enolate, the minus is on the oxygen, but it's also on the carbon down here. So that means this molecule can be basic at 2 sites. If it's basic here, it just goes back to where we started. And if it's basic here, it's going to go to a different product. So here's the ketotautomer. When you look at this, it's a little bit easier because I have a methyl here and a methyl here. And even though I have 6 hydrogens, they're all the same, they're all equivalent. So I can just use one and show the acid-base reaction. So my base, arrow starts there. We pick that up and put the minus on the carbon over here. Okay? So we get to the enolate. Again, this minus charge next to the pi bond, I can push this in and write a resonance structure with the minus on the oxygen, which is the one we had up above. Okay, so remember the enolates are just one structure that we draw 2 different ways. They're different than the keto-enol tautomers. Okay, so keto-enol tautomers are 2 different molecules that are isomers. They have the same formula. The only difference is the pi bond has moved to a new position and the proton has moved to a new position. So this could be a whole topic in itself, but we're not going to spend much more time on it than what we've done here. When you get to biochemistry, this is super important because the way glucose turns into fructose is it does 2 keto-enol tautomerizations. On the other hand, the intermediate is just one species right here that could react at 2 spots. So we could react at the oxygen or we could react at the carbon. So you should be able to write these resonance structures because you're going to need to do that to understand how things behave. Now here's a different kind of problem. So up here I'm saying we have some ambiguous competition. This is something you're going to see in chapter 9. Okay, so there's a little bit of stuff missing here. I have water. That looks like it could be a base because I got electrons there. And then I look over here. If water is a base, this must be an acid. And then if I look around, there's something missing. I don't know if you can see what's missing. Okay, this carbon looks good. Good. These are all methyls, but this guy in the middle only has 3 bonds, so it's missing electrons, and it should have a positive charge. Now when I put that in there, there's actually 2 targets for the water. The water could attack that carbon to join its electrons up because this needs electrons, or the water could come up here and attack this proton if I release these electrons, and if I release these electrons, it's pretty logical they would come in and share with the carbon that needs electrons here. So this is an ambiguous reaction. A common way to get organic problems is to predict what could possibly happen, and then you need to know all possibilities. That's a harder problem. Or they might just show you one of those possibilities and say, explain what happened. And then if you can explain the path of the electrons, you would be fine. So let's take a look at how we're going to do this. So if we come up here and take this proton off, that would be a Bronsted acid-base reaction, and use these electrons to fill in the pi bond. Okay, so that would look something like this. We would be done in one step using that Bronsted definition. So we would have our product here, which is an alkene. We don't worry about the hydronium ion. We'll just neutralize that on a workup. Okay, excuse me. This would be our product. What if we attack the carbon? If we attack the carbon is now fully satisfied. It has 4 bonds, which is what it wants. But the problem for the oxygen is now it has 3 bonds. And with 3 bonds, it's going to have a plus formal charge. Now, since one of these is a hydrogen, we could use the water that's out there and do an acid-base reaction, a Bronsted definition, and take that hydrogen off, and we would end up with the product that we were looking for, which in this case is an alcohol. Again, we don't worry about this. That would be cleaned up in the workup. So you'll notice 2 totally different products. One up here, we call this an elimination reaction, and one down here, we call this, well, actually the way I have it drawn, it would be addition, probably coming from substitution. Now, in acid-base chemistry, a lot of times these are equilibrium reactions, and so we want to have a little bit of a picture of that. So I show here generic base and HA, and I say the equilibrium here is favored on the product side. So notice K equilibrium is greater than 1, and it can be a huge number. Okay, it could be billions, but greater than 1 means it's a strong acid. What that's telling you is that we're starting at a higher energy, and then we're going down to a lower energy that's favored. That would suggest that the A- is very stable. Okay, when we get a reaction like this, because remember, a lot of times our base is water, and if this forms in preference to water, it must be a pretty stable anion. You can think of chloride, bromide, iodide, things like that. Okay, so this would be for a strong acid. We always tend to move to the side of the weaker acid and weaker base, because think about it. If you have a strong acid, it likes to donate its proton very well, so that's going to move you to the other side. Okay, say K equilibrium is less than 1. So now this is a weak acid over here we're talking about. So I changed it to Y just to be a little different. The reaction is still the same. Base picks up the proton, push Y away. So now the conjugate base is Y minus. But because this is a weak acid, Y minus must not be real stable. Okay, that's uphill in energy. And so the equilibrium equation expression would look sort of like this. We're going uphill in energy because this is less stable. And the higher we go up, the less stable this is, and there must be some reasons for that. And the reasons that we will look at will be inductive effects and resonance effects. Okay, so these are 2 possibilities for acid. A lot of our acids that we talk about are weak, and so they will be going uphill in energy, different amounts, and that's what we want to focus on. Okay, so these 2 reactions superficially look the same, but the K equilibrium is very different. And that will depend on the stability of the conjugate base. In this case, Y minus is less stable. In this case, A minus is more stable. Okay, we're going to get a little bit quantitative here. I know that's not always real popular, but we're going to have to use these Kas and pKas that you studied in freshman chemistry. Those of you that take biochemistry, you're going to come back and look at these all over again, including buffer problems and things like that. But we don't have to do that. Ours is just very qualitative in terms of understanding Ka and pKa. So I wrote the general reaction with water for all acids. Okay, so we're going to put a whole bunch of stuff where A is. We don't really care. Water picks off the proton and makes hydronium ion, and then the conjugate base over here. Now from freshman chemistry, you should be able to write a K equilibrium expression. They call that the law of mass action. And so I'd have the product of all the products, these guys here, divided by the product of all the reactants, these guys here. But what they do when they write a Ka expression is they assume that water concentration doesn't really change. A liter of water has about 55.6 moles, so we have 55.6 moles per liter. Hardly changes if we have a little bit of acid reacting. So we take that and we assume it's sort of constant and put it with K equilibrium and forget about it. We redefine this as Ka. So Ka is approximately the equilibrium constant. But now the only terms we're looking at are H3O plus, the conjugate base A minus, and the conjugate acid here. Okay, so we have a ratio of these guys. If this ratio is very big, then that means we have more of the stuff up here. It must be a strong acid. If this ratio is very small, we must have more of the molecular acid right here. This must be a weak acid. Okay, so you'll be able to tell just by looking at the number of Ka according to what we say down here. Now, we say if Ka is greater than 1, that's strong. But like I said, it could be a very, very big number. In fact, they have some things that are called superacids, and a Ka is written as 10 to the 20th. It doesn't really mean anything in water, and we're not going to worry about it. If Ka is less than 1, then that means we have more of this. It's a weak acid. And again, it could be very, very small, 10 to the minus 50. It's not possible in water, but it's just a number that we use to compare with other bases, with other negative charge. Okay. Now, we're going to quantify this a little bit more here so that this makes has some sense to the Ka and pKa, because pKa is a really weird concept. It seems like what's the purpose of it? It's because it's so confusing. So let's come over here and just take a look at logs and p concept for a minute. If I had 1,000, I could write the log. I could write that as an exponent 10 to the third. And if I had 1,000th, I could write that as an exponent 10 to the minus 3. What the log does is log takes the exponent part on a 10. So the log of 10 to the third is 3. It's just whatever that exponent is. Log of 10 to the minus 3 is minus 3. Now, if I come down and take minus log, basically I'm doing an inversion. I'm inverting it, so it's 1 over that. So in this case, minus log of 10 to the 3 is minus 3. And minus log of 10 to the minus 3 is plus 3. So very confusing to think about that. Then what p concept does is it says p is, whatever you're doing it, is the minus log of that. So if I looked at the minus log of this, and it's minus 3, I would say p of 10 to the third is minus 3. Okay, so the minus 3 looks small, but really it's a big number because it's a negative of the exponent here. And so down here I'd have p 10 to the minus 3. That would be plus 3. So 10 to the minus 3 is a small number, but notice that the p part of it looks positive, looks like a bigger number. So again, it's kind of confusing, but we're not going to even worry about that. What we're going to do is we're going to come back to something you had in freshman chemistry. Delta G equals minus 2.3 RT log K. Okay, so what we're going to do is we're going to put the 2.3 RT together. That's just a constant that we've talked about before. That's 1,400 little calories per mole, but we're going to make it 1.4 kcals per mole. So now this is 1.4 kcals. Minus log of K, hey, that's our definition of pKa. And so now what you see is we have this number right here, a constant, times the pKa, and that is delta G. So if delta G is in kcals per mole, delta G is 1.4 times the pKa. If we're just looking for the ballpark, we could sort of forget that 1.4. We can say delta G is the same as the pKa, approximately. Well, that makes the pKa have some meaning that we understand. So if delta G is positive, pKa will be positive. Or if pKa is positive, delta G will be positive. You can look at it either way. If you work with joules, kilojoules, then we'd have to multiply 4.18 times this. That would give us about 6. Okay, so I'm not going to actually use the kilojoules here, but if you do have to work with that, delta G would be 6 times the pKa. Okay. So now when we look at our energy picture, if we have the acid and we have a negative pKa, negative pKa means a negative delta G. Negative delta G means a strong acid that dissociates more than 1. Okay. On the other hand, if the pKa is greater than 0, then that means that delta G is greater than 0, positive number, and so the conjugate base will be less stable than the conjugate acid down here. Okay, and how big that is, okay, how positive it is, will tell you how far above the conjugate acid energy is. A bigger number will be a weaker acid. A smaller number will be a little bit stronger acid. Okay? So if pK is positive, delta G is positive. If delta G is positive, then this is a weak acid, and it does not dissociate more than K equilibrium of 1. So I drew some bases here, and I picked them all to be oxygen. Okay, so you can see all the oxygen minus guys are not the same energy. Okay, they're slightly different. And the range that, first off, oxygen's pretty good at carrying a minus charge. So they're all, not great, but they're 20 or less. So if I come over here and look at this is potassium T-butoxide, or T-butoxide base. I have 3 methyl groups here, all inductively donating in. And that's pushing electron density into something that's already 2 electron rich, and that's going to make it a little less stable. Now I can tell that when I come down and look at the pKa for the acid down here. So when this acid ionizes, its pKa is 19, meaning delta G is approximately 19 to make the conjugate base. For water, maybe you remember water. Water has a pK of 16. So water's not as high as this. I don't have any R groups here. So this is our reference point, basically, to make hydroxide. So hydroxide's not a very stable anion. You can tell because water would prefer to be water to a great extent. But it's 10 to the third times more stable than the T-butoxide. So T-butoxide is very reactive compared to hydroxide. If we go to some simple alkoxide, like ethoxide, it's very close to water. So in fact, I call this organic water. Okay, the specific compound here is ethoxide, but in general, we call these alkoxides from the alcohol. Okay, and the pK is about the same. So look, this is ethanol down here. This is water. I call ethanol organic water, and I call the ethoxide organic hydroxide. So these are real similar. Now all of a sudden, when we come over to this minus charge, it drops way, way, way down. So now the pK is 5. That means that that's 10 to the 11th different than these guys up here. Much more stable. So when you look at that, you want to have a reason in your mind for why that is the case. There's actually 2 reasons. We're coming from ethanoic acid, which you might know as acetic acid. In general, this would be carboxylic acids. But what we're seeing is that it's not such a big climb. And the reason is the minus charge that here is next to a pi bond. So I can push these in and push to the other oxygen. So the minus is actually spread over the 2 oxygens by resonance. And you can see how much that helps the stability. So this is going to be a much more behaved anion when we come to chapter 9. This will react different chemically than these guys up here in some cases. Okay, so here I took 2 nitrogen examples, kind of looking at the different atoms that we talked about. So notice the pKa values are way, way higher for the nitrogen minus because it's not oxygen. Oxygen's more electronegative. So the pKa for this guy, nitrogen minus by itself, is 37. Okay, that's huge. Remember, every number here is an exponent. Okay, we're sort of talking almost kcals. If I was talking kcals, I'd have to multiply by 1.4. So very, very high energy to make that anion. Very difficult. On the other hand, I can make the nitrogen minus here very easy. pKa is 5 for hydrazodic acid versus a simple amine. And the reason for this is, first off, I have resonance. Okay, I can push the electrons in and push them over here. And then I have 3 nitrogens carrying the minus, at least in the anion. This guy in the middle is always positive. But so I got a lot of electronegativity here in the 3 nitrogens, and I have resonance. So that makes it very stable. This is a very well-behaved anion, which will react totally different than this guy here in chapter 9. Just day and night, they're totally different because of their stabilities. Okay, here I have some carbon examples. So again, first one is cyanide here. Cyanide's pretty stable. Okay, it's sp hybridized carbon and nitrogen. That helps it out. We'll talk about that in a little bit. But also I have the nitrogen helping with the minus charge because of its electronegativity. I could have a triple bond between 2 carbons. So that would come from an alkyne, we need an H here, so they call it a terminal alkyne. Okay, whereas the acid here would be hydrogen cyanide. And then if I pull that proton off, I have a minus charge on the carbon, which looks pretty bad because carbon's not electronegative. But I do have the minus charge. The carbon is sp hybridized, which we'll see in a little bit. That's a very helpful thing to be sp hybridized. That's to be compared with a simple alkane type of CH bond. And this has a very, very high pKa 50, much higher than even the amine on the previous slide. Okay, so this is like the weakest acid that we can find, and this is the strongest base that we can find. It's a simple sp3 carbanion. So these are will both be important later on, but you can see there's different abilities to stabilize the minus, and that means different abilities to donate the electrons, which will be important in our chapter 9 topics. Okay, so let's compare some of these together. Okay, so I picked one of the guys from above and a different one from above, and I'm showing them as an acid-base reaction. So your first problem would be to decide what is the base, what is the acid. In this case, it should be pretty easy. I have a minus charge here on that super unstable sp3 carbanion, and I have an H over here on the nitrogen. So it kind of looks like this is the base and this is the acid. If that's the case, we should be able to fill in the arrows, bring the arrow over, make a new bond with the H, and then push these electrons away. If you were given these products, it would be super easy, because you could see I made a CH bond, and I broke an NH bond. So that would be easy. But if I just gave you these two, you'd have to figure out what's the base and what's the acid. Now we have to decide qualitatively which side is favored. And so we have a carbanion minus here, we have a nitrogen minus here. So simple electronegativity should tell you that the nitrogen minus is preferred, and this equilibrium should be to the right. Okay, that's qualitative analysis. Our arrows would look something like this. You would have to draw those, and then we would have the products over here. We would say this is more favored to the right. Okay, so if we had to pick, we would pick K equilibrium is greater than 1. That would be A. But what if we had the pKa values and the Ka values? Well, we already know that the equilibrium is greater than 1, but now we can actually quantitatively calculate it. You'll notice I have a Ka for the acid on the left side, and I have a Ka for the acid on the right side. But when we write a Ka expression, the acid's always on the left, so it would look like this. So if I wrote an equilibrium with this acid, I would just take the Ka directly. If I wrote an equilibrium with this acid, it's on the wrong side, so I would have to invert this. I'd have to write 1 over the Ka. All right? So if I write K equilibrium, I could take the Ka from this side, divided by the Ka from this side, and that would tell me the K equilibrium. All right? So acid 1, I take the Ka up here, 10 to the minus 37, and I divide that by the upside down one, which is backwards, 10 to the minus 50. When I look at that ratio, it comes out 10 to the plus 13. So even though this is phenomenally small, this is much, much smaller. And so the equilibrium is going to prefer the right side by essentially 100%. You can also do this in terms of delta G's, because remember this is sort of like delta G of this molecule here, and delta G to ionize it, the delta G. So if I did delta G, I would take pKa of, again, the left side, and I would subtract it because it's backwards, the pK of the left side, and I get 37 minus 50. Minus 13 kcal is a really negative delta G. All right? Let's do another one. So this time I gave you the Kas right away. So you could probably make an educated guess, although in this case you would be wrong. We would normally say nitrogen minus is better than carbon minus. And so we would predict, qualitatively, we would predict this on the left side. But this isn't normal carbon. This is sp hybridized carbon. And that is a much more electronegative carbon than sp3. So we better use the Kas to see what's going on here. Remember, this is the acid on the left side, so we're going to use its normal Ka, and then we're going to divide by the acid on the left side, it's Ka in the opposite sense. and that will be our K equilibrium. So if we put in our arrows, the base picks up the proton, push that away, so now we have a carbanion over here that's in an sp carbon. If we do the ratio thing, we have the Ka 10 to the minus 25 divided by 10 to the minus 37, and that comes out, surprisingly, 100% on the right side, 10 to the plus 12. Okay, that's a really, really big number. We could also do the delta G calculation. So I take the pKa of this guy, that would be 25. Remember the negative of the exponent. And over here I would take the pKa, and that would be the negative exponent. So I take 25 minus 37, and I get minus 12, which is very, very exothermic. So that would be products are favored. So you can see if you could write this out pretty quickly, it's not a lot of work. I'm just mentioning here that if you compare this to other problems we have to do, this is a lot quicker, but it has little conceptual stuff that's easy to mix up. Okay, I have another problem here. This time we're using water and this. Since I have a hydrogen on a nitrogen with a plus, I'm thinking this is probably the acid. Water is probably the base. So that'll tell you how to move your arrows. Can we calculate an equilibrium constant? Well, if we have the Ka's, which we do, then we could calculate what the equilibrium constant is. Okay, so let's take a look at that. Water picks off the proton, push that away. Okay, draw the conjugate base and conjugate acid that you form, hydronium ion. So this has a Ka, but it's backwards. And this has a Ka the normal sense. So K equilibrium will be the Ka1 here, 10 to the minus 5, divided by the Ka2, 10 to the 2. And so that comes out to be 10 to the minus 7. So what this tells us is that we are favored on the reactant side. We're only going to get a tiny little bit of this, not very much at all. If we use the delta G approach, then we would take the negative of this number, that would be 5, and we would subtract the negative of this number, that would be minus 2. And so 5 minus a minus 2 would be plus 7. We're going way uphill in energy. This would not be a favored reaction. Okay. But what if I turn this around? Then everything would just be the reaction from the right going to the left. And in this case, that's going to work great because those are the things that are favored. So this on this side, the acid would be hydronium ion, 10 to the plus 2, divided by the acid on the other side, 10 to the minus 5, and that would be 10 to the plus 7. You can see that's just the inverse of the one up above because we switched it around. We did it backwards. Okay, and the equilibrium constant would be, delta G would be minus 7. So every acid-base problem you look at is really two problems because you can go in either direction, forward or backwards. And you should be able to work it either way, qualitatively and quantitatively. You should be able to evaluate that. Okay, so I think I'll stop here, and I'll give you another, a second lecture for acid-base starting at this point to the end.